So, yeah, so recall that last time I formulated a somewhat imprecise conjecture that the L packets were parametrized by irreducible representations of this finite group, the set of connected components of the centralizer of the parameter divided by center. And the goal now is to be more precise and sort of characterize this map in some sense. So we want to see this as a pairing between the L packet and the centralizer. So we write it like this. And so S is in SV. And so the goal is to characterize elements in there plus their associated irreducible representation of the centralizer. And the way that this works is actually via certain linear combinations, which just by again, a Fourier inversion on this finite group is really the same thing. So this is a definition, and when S equals 1, there is no Whittaker datum in to decorate this, and so as you might expect, this means that this is not going to depend on the Whittaker datum, and so this just means that so this map depends on the Whittaker datum, but the dimension of the irreducible representation which is attached to a given pi doesn't depend on it. Okay, so when we have an element of the centralizer, what can we do?
Olivier, can I ask something? Why are irreducible representations of the centralizer or its component group a natural thing? Like, why is that showing now? How should we think about it?
You want a stacky answer? That's your...
Yeah, it's Q&A.
Yeah, Q&A, please. But I guess you want to look at the stack of parameters and then... Yeah. So think about it. I don't have a better answer than this, I guess.
Yeah, but maybe we can
discuss this answer. Discuss it later. So what can we do with an S in SV? So we can try to use it to factor. Well, when we have a non-trivial centralizer, it means that the parameter factors through some smaller subgroup. And so let's say that S is semi-simple. We can then define H0, which is the centralizer of this S, and take the trivial connected component. So this contains the image of SL2 and is also normalized by the image of the Veil group. And so if we let H be now the group generated by this H0 and WF, it's actually an extension of the Veil group by H0. I should have said maybe this one is a connected reductive group, this H0. Okay, and that's so extensions of. I had a better one. Extensions of the Veil group by reductive groups are. Ah, yes, that's the one. Of the Veil group by reductive groups are quite familiar now. So, so we have a map then from a morphism from the veil group to the outer automorphism group of H0. And it turns out that it factors through some finite Galois extension. And so from this pair, well, we know that this pair corresponds to a connected reductive group H over F that we can take to be quasi-split. And what we would like is also an isomorphism between H hat and H0, and so that the two morphisms to the outer automorphism group coincide. So of course we would like to extend this to an isomorphism between LH, so the Langlands dual group of H and H, and sorry, calligraphic H, I guess. So it's not always the case, but there's a way to reduce to this case. So just so maybe this should be called eta hat, even though it's not really the dual of something, but anyway. So just, yeah, assume that it exists, that there's a way to reduce to this case. And so this, the triple, so that's maybe S, H, and this L eta, maybe, sorry, now I can't forget about this calligraphic L and see this as an embedding of LH inside LG is what we can call an extended endoscopic triple. So that's the theory of endoscopy. And as I said, so now this was all to factor phi through some smaller subgroup. So phi is not now the composite of some phi h with this L eta. And the goal, well, the conjecture is going to be that the linear combination that is in the shadow here, okay, sorry. So this theta phi s can actually be deduced from this seemingly simpler thing here, but for phi h. And the way to express this is actually unconditional, so it's something that is well defined, the relation between the two. Okay, but so to do this, we need to relate conjugacy classes in H and in G. So from, I guess, L eta and, okay, essentially using maximal tori and Weil groups, because that's essentially the only things that really work when you go between groups and their duals. Right? That's more or less the only kind of functoriality that is obvious. So using identifications between these things for G and H, we get a map from semi-simple conjugacy classes in H of F bar and semi-simple conjugacy classes in G of F bar. And this map is actually gamma equivariant. So gamma is, we call that it's the absolute Galois group of F. But it's not a map from...
A question, please.
Yes.
So what is this map from WF to the automorphisms of?
So you have a short exact sequence. Yeah, it's just, so you take any element here, you lift it here, it acts by conjugation on this. There was a choice, which is...
And what is the bijection? Like, how do you go from the left-hand side to the right-hand side?
Sorry, from right to left?
So you have pairs H naught and parametrization?
Yeah, so I explained how to go from this to... From here to there. Okay, but so I also more or less explained that this outer automorphism group is also, if you choose any pinning of this H0, then it's the same thing as the automorphism group of H0 with the pinning. Okay, so choose any pinning, then you have an action of gamma on the group with the pinning, and that's, well, a base root datum, take the dual, and there's a unique quasi-split. Okay, so this is, we have this gamma equivariant map, but it's not a map between, from semi-simple conjugacy classes in H of F to things in G of F bar.
Olivier, just to clarify, this assumption here is in general wrong, right?
Yes, but it's not
simplifying assumption for you.
Yes, but it's not. It's a solvable problem by Z extensions, essentially.
Maybe you should repeat what the problem is.
So the problem is this might not exist. This extension of eta hat you cannot always identify this H with an actual Langlands dual group, but up to taking a Z extension of H, it works. Okay, so here already we see that it would be nicer to work with a stable conjugacy. So if we take let's say delta and delta prime, so first delta in G of F is strongly regular if the centralizer in G is a torus and delta and delta prime in G of F strongly regular or stably conjugate if they are conjugate in G of F bar. There's a notion of stable conjugacy with not a strong regularity assumption, but let's not worry about that. And you can see, so if you let T be the centralizer of delta in G, so that's a torus here, the set of conjugacy classes delta prime, which are stably conjugated to delta, so these are conjugacy classes in G of F, just to be explicit, you can write it as, using Galois cohomology, as a kernel like this. And I'm sorry that it's in the corner, but as the kernel of H1 for T to H1 for G. Just by, so you take an element of, well, yeah, you take the co-boundary of an element conjugating delta into delta prime, and you get this. And okay, so now we're going to use the map between semi-simple conjugacy classes in H of F bar and G of F bar now to get a correspondence between stable conjugacy classes. Okay, so now it becomes interesting to have a good understanding of this Galois cohomology group. So recall that we have the Tate-Nakayama isomorphism. So first for tori. So this is isomorphic to you take the co-invariance of the co-characters of T and the Galois, and then you take torsion, the torsion subgroup. And this can be reinterpreted as the characters of the group of connected components of gamma invariant in T hat. And a theorem of Kottwitz, I guess F is non-Archimedean. Just to simplify.
For torus, you need non-Archimedean. I think for G you need non-Archimedean, but for P you don't, yes?
Yes, but I'm going to forget this assumption a lot today, I think. So in the theorem, for example, there's an Archimedean version, but I'm not going to bother to state it. But yeah, thanks. So let's say F is always non-Archimedean today. And sometimes I'll say this works for real fields, and that means an analog works for real fields. Okay, so the theorem is there's a unique way to extend this to get maps like this for connected reductive groups. Which in a way that is functorial, but only partially functorial. Well, yeah, partially functorial. So let's say for torus embeddings, maximal torus embeddings. And central isogenies. Okay, so there's a nice interpretation in terms of dual groups of these Galois cohomology sets. Well, actually, well, they're pointed sets, but they turn out to be groups. And so this writes. So the proof of this is so in 2 words. Essentially, you can see that if G is semi-simple, simply connected, this says that H1 on the left vanishes, and that's actually a nice theorem of Kneser that's much older than this. And the general case is by reduction to this case using central isogenies.
So now you need the assumption, right? But maybe there's an arrow in one direction.
Which assumption?
On non-Archimedean.
Yes.
You wrote it there. Yeah, okay.
Yes, so there's always a map, and in general you can describe the image, but no. Okay, so using this and much more, so Langlands, Schellstadt, and Kottwitz defined transfer factors. So yeah, let's just say transfer factors. So that's a function. So we are back to the previous situation. like this. So here, strongly regular is what I defined earlier, and G strongly regular means an element of H such that, so a semi-simple element of H, which when you map it, well, this map at the top, it is G, strongly regular in G. Should have given a name to this map, I'm sorry. Call this M. And supported, so that's invariant under conjugation by it's actually more invariant than that, but anyway, and supported on the set of pairs gamma delta, such that delta belongs to the image of gamma. Okay, so now I can state the conjecture, the more precise conjecture. And so just to recall the assumption, so G is quasi-split. We have a tempered parameter. And so the first part is that the linear combinations of Harish-Chandra characters that are called S theta are actually, so just to remind you, these are functions like this. They are stable, meaning that they are invariant under stable conjugacy. And second, for any semi-simple S in the centralizer, you recover this, and so for any delta strongly regular, you recover the value of this particular linear combination at delta. Via the this stable thing for what I denoted phi h, using as kernel this these transfer factors. Okay, so of course this I just said that the support of this is the set of matching pairs, so this sum is actually restricted to the set of gamma, which map such that M of gamma contains delta, and it's actually a finite sum. Okay, so just a couple of remarks. If you believe in this conjecture, then now everything is pinned down by these stable, yes?
So the support of the transfer factor, delta is in M of gamma. What is that M?
M is the map that I... that I had difficulty writing. Okay. So yes, so you can see on this that actually everything is now determined by the S theta phi, and the stable things S theta phi are, well, they're close to being just the L packets, right? So you have the dimensions of the irreducible representations of the centralizer occurring in there. Yeah.
In this formula, does H depend on S?
Yes, so I'm using the notation that I introduced before. So from S, you deduce this extended endoscopic triple and blah, blah, yeah. Yes, so apart from, say, the dimensions of the irreducible representations of the centralizers associated to the elements of the L packets, that tells you that the internal structure is in fact determined by the L packets. Maybe I should have added here that it's actually conjectured that these are the minimal, in some sense, the minimal linear combinations that are stable, in the sense that if you have some linear combinations of Harris-Chandra characters of irreducible representations which is stable, then it's actually a linear combination of such things. Okay. Well, not so interesting remark, but just because it has confused me for a while. You have a choice of S here, and but this should actually only depends on the connected component in which S sits. So there's actually like a parabolic reduction to this case to show that it doesn't that the right hand side doesn't only depends on the connected component in which S sits as well. Another thing is that, so contrary to what I said about the, say, unrefined local Langlands conjecture, this now doesn't reduce so easily to the case of discrete series. So if you go back to the way tempered representations were classified in terms of discrete series, you now have to understand the reducibility of the parabolically induced representations and relate that to, well, essentially the difference between the centralizers in a levy and in the whole of LG. So there's something non-trivial here.
Sorry, I have a question.
Yes.
So if I understand things correctly, you're interpreting these Harris-Chandra characters as functions. Is that right? Like S theta p is a function of...
Yes, I'm just treating them as...
So is this using this like representability theorem, which is only true in character 3, 0?
Yes. So there's a way to state the same thing with functions instead, but you need the transfer conjecture. It's also only known in characteristic 0, I think.
Okay, yeah, I just wasn't sure because you said that was...
but it's known. Okay. And so now, of course, what we would really like is to give explicit formulas for this S theta phi. And from the case of real groups, you can actually guess that you should have nicer formulas for these things if you ever have to have formulas. So now I can talk about theorems. So known cases. So there's when F is R, so I should have said before, but so Langlands constructed the map LL, and Schellstadt established the internal structure of L packets. So there's SL2, which is a precursor to the theory as well. So and a very nice example, because many of the things which are complicated in general or already complicated for SL2. And then there are, so the quasi-split symplectic and special orthogonal groups by Arthur, and the quasi-split unitary groups using the same method by Mock. So the Arthur's method is using the stabilization of the twisted trace formula, and so in this case, these stable linear forms here are characterized by twisted endoscopy. So there are twisted endoscopic character relations of this type, which pin down these things. Well, for SO2n, it's really up to outer automorphism, but let's not get into this. There's GSP4. Again, Takeda and Chan and Gan. And okay, so there's more to come, but the rest is, I think, known for non-quasi-split groups as well. So I'm keeping a few things for later.
The work of Arthur and I think all the analogous work are still conditional on some results to be published, right?
Yeah. So it's conditional on the full version of the. There's one small case of the, one case of the fundamental lemma, and also things which were announced by Arthur.
Asked about applications of the trace formula.
That's a nice application of the trace formula. Yes.
Bottom three are just for like p-adic equivalents, right?
There's no point talking about the reals anyway now. Yes, this is sorry. Thanks. Yes, p-adic. Well, okay. So non-quasi-split groups now.
Sorry, can you say what is in this Chen-Gan paper that's not in Gan-Takeda?
So Gan-Takeda is using several theta correspondences, and then Chan and Gan proved the endoscopic character relations also using the stabilization of the trace formula. Where am I now? Yeah. I think this one. Sorry?
7?
Yes. But I didn't prepare. So, this book, Memoirs of the IMS. Yeah, I guess I do. Thanks. Should have known. But I'm not sure. Yeah. Did they prove? I forget. If they proved the endoscopic character relations, I don't think so. Maybe I'm not remembering.
Change it up to continuity.
Good. I'm probably forgetting other results. Okay. So, non-quasi-split groups. Okay, so recall that two Langlands dual groups are isomorphic if and only if G2 is an inner form of G1. And okay, so in particular, in this case, they have the same Langlands parameters, so there should be some relation between the they're L packets. And from what Labes and Langlands proved, they actually handled the case of inner forms as well. It's more or less clear that you have to modify this S phi in the case of inner forms. Okay, and so for a long time there was unfortunately no normalization of transfer factors in general. So these functions were only known up to a non-zero scalar, if you want. So that was a difficulty for even formulating this in general.
Can I ask just one clarification? When you talked about these non-cases, do you mean these groups are the group G or the group H?
So that's G. And actually, in all these cases, H is more or less of the, it's not more complicated than G in some sense. Okay. So for example, for the classical groups, H is going to be a product of classical groups.
Thank you.
And that's how it's possible to even formulate the thing. Yes. So Vaughan's idea is to define one big L packet pi phi using all inner forms at once. And we saw in the, so because we understand, well, we have a nice thing in the case of quasi-split groups. So you want to use a quasi-split group as a base point. And we saw in the first lecture that, unfortunately, the automorphisms of an inner twist is the group of rational points of the adjoint group, and this thing acts non-trivially on the set of isomorphism classes of irreducible representations. So that doesn't quite work, but the solution is to use pure inner twists. And so you take, as before, so let's say that this is the quasi-split group G. So you want a G prime and a psi, and you enrich this with a Z. Which is a one cocycle taking values, in G, that's the point, and lifting the one cocycle taking values in the adjoint group.
Sorry. Could you repeat why Vaughan's idea does not work?
No, it does work, but you have to use pure inner twist in a sense.
Right, but what was the reason?
So the reason is that if you take automorphisms of this thing, so automorphisms of this inner twist, that's G prime add, take the F point, and that acts non-trivially on the set of irreducible representations of G prime of F. Okay? It's a small thing, that, like the difference is finite, but still it doesn't work. So for this reason, you want to introduce pure inner twists. So you rigidify the situation like this. But now you have a new problem, which is that this thing is not surjective in general. So you don't capture all inner twists. And in fact, by Kneser's theorem, if G is semi-simple simply connected, what you capture is nothing at all. Well, just the original quasi-split group. So that's why I was telling you SL2 is already interesting. Okay, so now we have a new problem, so we need a new solution. And that's to use marginal Galois cohomology groups. And Okay, so when F is R, Adams, Barbash, and Vaughan gave a kind of ad hoc solution because the Galois group is not so big in this case, so you can work out cocycles by hand. And when F is p-adic, Kottwitz suggested using isocrystal with additional structure, so this B of G, which is something larger than this. Okay, and this was this works. So and this was used in the early works by Tasho, and unfortunately, it's still not general enough in the sense that you get something bigger here, but it's still not subjective here.
So this work means that you rigidify the problem, right?
Yes, so I'm not being precise yet, but I'll be more precise later. So then finally, we have so Tasho defined the so-called rigid inner twists that are so a generalization of this thing here that subjects onto here. And this actually all of these cases they all fit into the same framework of Galois gerbs. So they're all Galois gerbs. So let me explain this. Sorry, I should have said then in characteristic. So this is still p-adic, and non-Archimedean characteristic P. Okay, I want to put this into brackets because then it's not true that it's a Galois gerb. But the characteristic P case was worked out by Peter Dillery. Okay, so but all the other ones in characteristic 0 are Galois gerbs. So I'm not going to talk about actual gerbs in the Stacky sense, but just give you the concrete kind of elementary version using group cohomology. So we're going to need an algebraic, group scheme U over F. That's a projective limit over a countable set of UIs, where UI is a multiplicative group of finite type over F. And a Galois gerb is then, and here you see that we need characteristic 0, an extension like this of topological groups. Where gamma has the obvious, the natural action on U of F bar. And such an extension corresponds to a class in this H2. Okay, so yeah, because, well, I wasn't very precise with the topology, but if you start from a continuous two-core cycle like this, you actually construct this E set theoretically as the product of this and this. And that actually gives it a topology, because this has a pro-discrete topology and this has a pro-finite topology. And you define the multiplication using the 2 cocycle.
So this U is something very specific that you're not...
Yeah, all of these things fit into this framework, and I'm going to give you this U later.
Why is it obvious that I
well, no, the problem is it depends if F bar is separable or algebraic closure, I guess. But yeah. Sorry, no, it's obvious if U is not, say, if the UIs are finite, for example. Like if a UI is mu p in characteristic p, you can guess that you're gonna have problems, right? It's not very. You were asking?
Well, I asked what was obvious. I didn't hear the beginning of it.
No, I was saying that it's kind of obvious that you're going to have difficulties when f has positive characteristic, but I was thinking about the case where the UIs are finite. Or you think of the case where a UI is mu p, for example. Okay. So then, we have a subset of this, which is the set of 1 cocycles whose restriction to U of F bar is given by an algebraic morphism over F bar between U and G. So we have a map nu from this H1 alg G to harms like this. And you can check that because of the cocycle condition, the G of F bar conjugacy class is actually gamma invariant. So you have a map like this. And the kernel of nu, is what's called H1 basic EG. And this one actually maps 2 harms from U to the center of G. Sorry. I don't want the kernel of nu. So it's the set of classes such that nu of C takes values in the center. So yeah, we have 3 cases to consider. First, the case of pure inner forms. Second, the isocrystal case where the group of characters of U is Q. And so in this case, the H2 is, sorry, I was confused. This, and you take the class Xi corresponding to 1, and you get an extension E iso. And so that's the isocrystal case, so B of G. And finally, the case where the group of characters of U is smooth functions from gamma to Q over Z with the obvious action of gamma. And in this case, the H2 is isomorphic to Z hat, and you take the class corresponding to -1. And that's the rigid Galois job. So we have generalized Tate-Nakayama morphisms. So the first one is a theorem of Cotfit. So in the isocrystal case, this basic H1 is isomorphic to, so it's quite similar, but you just don't take the group of connected components. It's quite nice. And in the rigid case, so it's more convenient to take a finite subgroup of G of Z, of the center of G, sorry. And so let G bar be the quotient, and Z of G bar hat plus is the preimage of gamma invariance in the center of G hat in the center of G bar hat. And then the result is, so now we restrict, because it's simpler to state, to the basic cocycles, such that the morphism from U to the center of G factors through Z. So that's this notation here. And this is isomorphic to characters of pi 0 of this Z of G bar hat plus. Ah, sorry, I didn't. This is ISO, the isocrystal version. So we already had Tate-Nakayama in the pure case. Okay, so now the conjecture, still with this assumption, I guess. So let's state the 3 at the same time. So G is quasi-split with a Whittaker datum W, and so we need different notations in all 3 cases. So they all look a bit the same but slightly different. So that's the pure case. Then we have ISO case. So this is not really necessary, but just to point out that because U is a protorus in this case, morphism from U to the center of G is always going to map through this trivial connected component. So now we have this slightly weird definition. And so in the rigid case, we take a finite central subgroup as before. And we do something similar as we did for Z of G bar hat plus for the centralizer. And this J ridge is now again phi 0 of C of G bar hat plus. And now we define the big, so Vaughan's dream, the big L packet as, well, so we need tuples. So G prime C is an inner twist of G, and Z is a one cocycle lifting the same thing as usual, and pi is an element of the packet for phi, so phi is tempered. So we take these four tuples up to a notion of isomorphism that I let you imagine. And the conjecture finally is the following thing, this commutative diagram that extends the previous iota W. There's an obvious restriction map from here to characters of J something. And here, if you just record the class of this Z, so this is restriction, you get an element of H1. And yeah, you should have a commutative diagram like this.
Do you want to say pi is in the packet of G prime?
Pi, sorry?
Yeah.
That's what you meant? Thanks. Okay. And, well, I should say, I don't really have time, sorry. Plus endoscopic character relations. So which implicit in this is the fact that you can actually normalize, so define the transfer factors using these Tate-Nakayama isomorphisms. Okay, so just maybe a concluding remark. So there are three versions. In practice, you want to use the simplest one, which is either this one, or if you cannot, this one, or if you absolutely have this one. Because, well, it gets more and more complicated. So even though I stated that U should be a projective, well, projective limit in general, actually in the second case you can reduce to just a torus, so it's simpler than the third case. But okay, so the third version is the most general one. Yeah, and that should also prove that if you prove the conjecture in the isocrystal case, in say in an isogenic class of groups G, then it actually implies the rigid case. Okay, so maybe, yeah, and I should maybe conclude with a known case. So work of U, Adler, Spice, Caletta, Finsen. So for phi supercuspidal, let me give you the short version. So it's for phi supercuspidal, so recall that this means that phi is discrete and the restriction to SL2 is trivial and P is big, then this is actually no. Okay, there's also the case of unitary groups by Caleta, Minguez, Chin, White, and also F equals R. So essentially by that's the work of Shellstad. But it's a bit funny because it was proved before it was really formulated like this. Okay, sorry for being late.